When you first build a neural network, it doesn't know anything. Its internal weights and biases are completely randomized, leaving it blindly navigating the data and turning out terrible, unusable predictions. The core engineering challenge of machine learning is figuring out how to force that randomized code to systematically recognize its own errors, correct them, and actually learn. To do that, developers rely on a mathematical algorithm called gradient descent. It acts as the primary optimization engine driving modern AI. This process forces the network to align its internal weights with the training data, evolving the code from static noise into a functional architecture. We visualize error using a cost function, a 3D landscape where high peaks are terrible predictions and deep valleys are perfect accuracy. The algorithm seeks the absolute lowest point. Flattened into a 2D topographical map, the smallest ring's center represents this lowest possible error. Because our algorithm is essentially blindfolded, it has to feel its way down. It calculates the derivative, or the gradient, of the cost function to determine the exact slope of the mathematical ground directly beneath its current position. Using that slope calculation, it steps strictly in the direction of the steepest downward trajectory. The physical size of that step is dictated by a setting called the learning rate, or alpha. This is a hyperparameter, a strict rule configured by the human developer before the training even begins. If you set the learning rate too small, the algorithm will safely reach the bottom of the valley, but it will take an agonizing number of tiny steps, consuming massive, inefficient amounts of computational time to get there. But set the learning rate too high, and you hit a catastrophic failure state. The algorithm takes a massive leap, overshoots the valley bottom completely, and bounces higher up the opposite slope. This triggers an exploding gradient that breaks the model. Correctly tuning this learning rate is the most critical balancing act a developer performs. They must calibrate perfectly between computational speed and mathematical stability. To monitor this unseen journey over thousands of iterations, data scientists use a specific data visualization. This chart shows the error rate, loss, on the y-axis, tracked against training iterations on the x-axis. A healthy curve plunges sharply during initial steps, then smooths out. Eventually, the line flattens completely into a horizontal path. This is convergence, proving the lowest possible error. Reading this curve allows engineers to verify when a model is successfully trained, letting them stop the process before burning through expensive server compute resources. Basic regression models have smooth, simple, bowl-shaped terrain. Deep learning networks, however, create rugged, unpredictable, multidimensional landscapes filled with traps. The first major terrain trap is called a local optimum. These are shallow dips in the landscape that catch the marker. This tricks the algorithm into thinking it has reached the absolute bottom of the entire mountain, when the true lowest point sits much further away. The second trap is the saddle point. This is a flat, plateau-like zone where the mathematical slope drops to zero. Without a downward gradient to follow, the descent stalls out entirely. Getting stuck in either of these traps causes the learning loop to terminate prematurely. The developer is left with a permanently underperforming model. Because of this, advanced machine learning requires engineering-specific strategies to force the algorithm to escape these mathematical dead ends. To survive this rugged terrain, developers use different variations of gradient descent. These types manipulate exactly how the algorithm processes the data. The first method is batch gradient descent. The algorithm calculates the slope using the entire dataset before taking a single step. It is highly stable, but that strict stability makes it prone to getting stuck in local optima. On the opposite end of the spectrum is stochastic gradient descent, or SGD. It evaluates only one single data point per step, making its trajectory incredibly fast and highly erratic. That chaotic, noisy jumping behavior provides the kinetic energy necessary for the algorithm to bounce out of local optima traps and keep moving down. Today, the industry standard is mini-batch gradient descent. Instead of taking the whole dataset or just a single point, it processes small, manageable chunks of data at a time. Mini-batch balances the computational efficiency of the batch method with the trap-escaping kinetic noise of SGD. Ultimately, gradient descent is an iterative process where active calibration and navigation determine how close the model will ever get to its lowest potential error.